In this lecture, we'll discuss the Jordan canonical form representation for linear system, linear time invariant system, and please note that we are considering a causal system. So consider the system shown here. So in this representation is of nth order. There are p number of outputs and m number of inputs. A, B, C, D are constant matrices with appropriate dimension. So this is what we have, and we want to see how this system can be represented in the Jordan canonical form. So when we talk of Jordan canonical form, we are basically talking of a state space representation where the corresponding A matrix will be the Jordan form of the matrix A that you have got with the state vector x. Okay, so now if you recall the lectures on Jordan forms of a square matrix, we had seen how that Jordan form can be computed and what is the similarity transform matrix that takes a matrix A to its Jordan form. So if you recall, what we had is a similarity transformation matrix P, which is constructed out of the eigenvectors of a n cross n dual matrix A, and this eigenvector constitutes of the ordinary eigenvectors and the corresponding generalized eigenvectors, of course arranged in the order in which they are being generated. Okay, so P is basically a matrix whose columns are the eigenvectors of A, ordinary or generalized. Okay, so once we have this P, we can have a state vector Z which is related to the state vector x through this similarity transformation matrix P, okay, which is Z equal to P inverse x. Then in that case, the state space representation with respect to the state vector Z is P inverse APZ plus P inverse BU, and the output is CPZ plus DU, right? Where the P inverse AP is now the Jordan form of the matrix A that you had in the state vector X representation. Okay, so this Jordan form, which is I am representing here as JA, is essentially or will essentially have Jordan blocks corresponding to the eigenvalues of A. Okay, now what is the benefit of this? So once we have this particular similarity transformation matrix P used, and if we express the matrix A in its Jordan form, essentially the state space representation that we are using would be the Jordan canonical form. Okay, now this Jordan canonical form helps in dividing the system into independent subsystems. Okay, so each Jordan block will correspond to a subsystem. Okay, also if a system is in its Jordan canonical form, then without forming the controllability or the observability matrix, just by observing the equations that you have representing the linear system, linear time invariant system, you can actually one can actually conclude whether the system is observable or whether the system is controllable or not. Okay, so we'll see how this Jordan canonical form can be formed and how the conclusion about observability and controllability can be drawn just by seeing the matrix structure, okay, through some examples. So consider this system. X dot is of this form and y is of this particular form. Okay, so what we need to do is first find the eigenvalues of A and then find the eigenvectors corresponding to the eigenvalues of A, then form the similarity transform matrix P, and then perform the state vector transition so that we get the Jordan canonical form. Okay, so the matrix A is this, whose eigenvalues are going to be 1, 1 and 6. So eigenvalue 1 is repeated twice and eigenvalue 6 is 1. So for eigenvector of lambda 1, if we compute the OEV, what we get is there is only one ordinary, all the ordinary eigenvectors are going to lie in the span of 1, 0, 0. So this is the ordinary eigenvector v1 that I choose. Though now since the eigenvalue 1 is repeated twice, the remaining eigenvector has to be a generalized eigenvector generated from 1 in this particular case. So if I find out the generalized eigenvector, it turns out to be basically all the eigenvectors in the span of this. Okay, so this is what I have. Now we have got the two vectors corresponding to the eigenvalue 1. Similarly, we can compute the ordinary eigenvector for the eigenvalue 6, and this is what we have with us. So the similarity transformation matrix P that is required for the Jordan canonical form representation is found out of these three vectors and is given as this. Okay, so this is what your P is. The first column is V1, the ordinary eigenvector of eigenvalue 1. The second column is V2, which is a generalized eigenvector of eigenvalue 1. And the third column is V3, which is the ordinary eigenvector of eigenvalue 6. Okay. With this P, if we find the Jordan form, then the Jordan form turns out to be of this form. Okay. And the corresponding B matrix would be P inverse P, which turns out to be this, and the corresponding C matrix turns out to be of this form. So what is the Jordan canonical form representation of this particular system that was given to us? So Jordan canonical form representation of the system given is as shown here. So if you see the matrix A corresponding to the state vector representation in the state vector Z is in the Jordan form, and the corresponding B and C matrices are as shown. Now, if we compute the controllability matrix, then and check the rank, it turns out that the rank of the controllability matrix is 2, indicating that the system is uncontrollable. Similarly, if you compute the observability matrix out of this and compute the rank of the observability matrix, it turns out that the rank of the observability matrix is also 2, so it is unobservable. Okay, if the rank of these matrices, the observability matrix or the controllability matrix, had been 3, which is equal to the order of the state space representation, then in that case the corresponding the system would have been observable, or the system would have been controllable respectively. Okay, now we'll see how we can conclude that the system is controllable or observable or not just by seeing the Jordan canonical form and without actually evaluating the observability or the controllability matrix. Okay, so you observe here that the Jordan block corresponding to the eigenvalue 1 is just this, and the Jordan block corresponding to eigenvector 6 is 1. So there is one Jordan block corresponding to eigenvalue 1 and one Jordan block corresponding to eigenvalue 6. Okay, now let's say that this, I can divide it like this. So this is the Jordan block for eigenvalue 1, and this is the Jordan block for eigenvalue 6. And now the last row here corresponds to the Jordan block corresponding to eigenvalue 6. And similarly, for the Jordan block corresponding to eigenvalue 1, this is the block that you have here, everything upstairs this red line. Okay. So for the Jordan block corresponding to eigenvalue 1, observe the last row of this particular block. The last row corresponding to the Jordan block of eigenvalue 1 is a non-zero vector. It is 0, 2, which is a non-zero vector. Okay. And similarly, the row corresponding to the Jordan block of eigenvalue 6 is actually a 0 vector. Okay. So this indicates that the system is uncontrollable. What indicates is basically if the eigenvalues of a given system have only one Jordan block associated with it, then for each Jordan block, accordingly break the B matrix and check the last row of each piece of the B matrix corresponding to each Jordan block. Okay, and check whether they are non-zero vectors or not. If they are non-zero vectors, then if all of them are non-zero vectors, then essentially you have a controllable system. If any one of them is a zero vector, then you have a uncontrollable system. So in this case, the Jordan block corresponding to eigenvalue 1 has this 2 cross 2 block of the B matrix, of which the last row is a non-zero vector. But when we observe the Jordan block 6, then the row corresponding to it is 0 0, which is a zero vector, so the system is uncontrollable. Okay, a similar analysis goes for observability. However, in this case, instead of rows, we piece the C matrix again with appropriate size. So in this case, the C matrix would be broken as this. So the 2 cross 2 part corresponds to the Jordan block corresponding to eigenvalue 1, and the 2 cross 1 part corresponds to the Jordan block of eigenvalue 6. Now in case of the Jordan block of eigenvalue 1, we see the first column associated, first column of the C associated, and it turns out that it is 0, while the Jordan block of 6 is associated with a non-zero column of C. Okay, now because of the association of a zero vector from C to the Jordan block corresponding to 1, it indicates that the system is unobservable. Okay, to make this a little clear, we'll see a few more examples. So if you consider this system, which is a 4 cross 4 system, okay, so here in this 4 cross 4 system, this is already in the Jordan canonical form that we have. Now there are two Jordan blocks corresponding to eigenvalue 1 and one Jordan block corresponding to eigenvalue 2. So for each Jordan block, we'll piece the B matrix here. So if you piece the B matrix, the first block is of size 2 cross 2, so the B matrix will have 2 rows in it. The second Jordan block is of size 1 cross 1, so the B will have 1 row in it. And the eigenvalue 2 has a Jordan block of size 1. Again, there will be 1 row from the B matrix corresponding to this particular Jordan block. Okay. So now if you want to analyze controllability in such a case, we'll first check for each eigenvalue. So corresponding to 1, there are two Jordan blocks. Now the Jordan block that you have here, which is of 2 cross 2 size for eigenvalue 1, the corresponding last row here is this. This is the last row. Similarly, so for this is the last row. Similarly, for this particular Jordan block, this is the row that we have. Now we have two Jordan blocks for one, and for each Jordan block we have identified the corresponding rows from B. Now check whether these two rows are linearly independent or not. In this example, it turns out that the rows are linearly independent. Okay, so the eigenvalue 1 in this case, or rather we will not say that. So in this case, the two rows corresponding to the two Jordan blocks of eigenvalue 1 are linearly independent. Similarly, for eigenvalue 2, there is no other Jordan block, so you just have to check whether the row corresponding to eigenvalue 2 is basically a non-zero vector or not. Okay, so for 2, the corresponding row is non-zero vector, and for 1, for both the Jordan blocks, we have two rows of B which are linearly independent. So this essentially indicates that the system is controllable. Okay, so how can you conclude controllability from the Jordan canonical form? It is this: consider one particular eigenvalue and take the and observe the Jordan blocks of each eigenvalue. Okay, for each Jordan block, for the size of each Jordan block that you have, piece the B matrix. Now, corresponding to each Jordan block, take the last row of its corresponding piece from the B matrix. Okay, do this for all the Jordan blocks of the same eigenvalue. Once you have done this for all the Jordan blocks of the same eigenvalue, once you have identified the rows in B corresponding to Jordan blocks in the same eigenvalue, the last rows specifically, take all the last rows for the eigenvalue and see whether they are linearly independent or not. If they are linearly independent, well and good. Okay. If they are not linearly independent, the system will be uncontrollable. Now, this linear independency should hold for all the eigenvalues. So, let's say that for in this particular example, if there were 3 Jordan blocks corresponding to 1, given that the size, given that the rows of B have 2 elements, then once you have 3 Jordan blocks corresponding to 1, the moment the third row comes in, it will be like you have 3 vectors which have 2 tuples each, and you are trying to check for linear independence, and they will never be linearly independent. Okay, and hence what happens is the Jordan blocks for the 3 Jordan blocks of 1, the system will not be controllable. Okay, if you check for observability, what one can do is again partition it corresponding to the Jordan block 1. This is the second partition for the Jordan block 1, and then you have for the Jordan block 2. Okay, now check the first column. So if you check the first column corresponding to the first Jordan block of 1, it is 1 0. The first column for the second Jordan block is 0 1, and these two columns are linearly independent. So the columns corresponding to the first columns corresponding to the Jordan blocks of 1 are linearly independent. Similarly, for 2, there is only one column here, so this one column is of course linearly independent with itself. Basically, it need not be a non-zero vector. Okay, so it turns out that whatever columns that you have chosen corresponding to eigenvalues, they are linearly independent, and this is true for all eigenvalues. Hence, the system is observable. Okay, I will do a slight modification to see what actually happens if there is a small change. So what I'm doing, if you also compare the system upstairs and the system downstairs, I modified the third row in the B matrix and the third column in the C matrix. Okay, now given this particular change, my Jordan block for 1 is still the same. There are 2 Jordan blocks, one is of size 2 cross 2 and one is the size 1 cross 1, and the next Jordan block for eigenvalue 2 is of the size 1 cross 1, and the corresponding division in B is this. Okay, now observe the last row. The last row here for Jordan block 1 is 0 1, and the row for the second Jordan block of 1 is also 0 1, and these two are not linearly independent, so the system is not controllable. Okay, similarly, if we piece the C matrix in terms of the with respect to the size of the Jordan block, then what we observe is the first column for the first Jordan block 1 is 1 0, and the first column for the second Jordan block 1 is also 1 0, and they are not linearly independent. Okay, due to which the system is unobservable. Okay, so as you see, just from the Jordan canonical form, you can actually say what say about the entire system, whether it is controllable or not, whether it is observable or not, without forming the observability matrix. Okay, so I says that you take a few more examples, try to see how this works out and verify the same. In fact, for these systems that we have discussed, verify the claims of controllability and observability by checking the corresponding controllability and observability matrices as well. Okay, so we'll stop here. Thank you.